Well, good evening, everybody. Today, the main topic is something called divisibility. Divisibility. Okay, so I want to start really low level. Just what is it exactly does the term divisibility mean? Well, first of all, we are only considering integers. We are not considering fractions or irrational numbers in this process. So when we talk about divisibility, we're only going to talk about divisibility of integers because that's the definition. Now, if I said what's 1/2 times 1/3, I know that's 1/6, but that's not what we mean. We don't say 1/6 is divisible by 1/2 and 1/3. So the way we look at it, if I ask the question, all right, is 4 a factor of 20? Is 4 a factor of 21? This is a simple question that comes up in every level of mathematics. There's really not a whole lot of thinking takes place. Anybody want to answer these questions? Want to try? Is 4 a factor of 20?
Yes.
Is 4 a factor of 21?
No.
No, both answers are correct. Now it's the why. Why would that be the case? Well, in the first case, 20 over 4 equals 5. We have no doubt about that. But in the second case, 21 over 4 equals 5 1/4. So we said yes in the first case, we said no in the second. What does the second one have that the first one doesn't have? What is that guy called?
Remainder.
Remainder, perfect. This is the definition of divisibility. Divisibility, first of all, we're only considering integers. We say that something's divisible if there is no remainder, or if the remainder is 0. Okay, so sometimes we forget, because remember in algebra, we sometimes do this with polynomials. We'll say a polynomial divided by another polynomial equals something either with a remainder or without a remainder. So if I gave you a quadratic and I asked, is it divisible by, say, some linear factor, you would answer yes or no based on the fact whether there's a remainder or not. So let me give you a different example, because it's still the same rules. If I said, is x squared minus 3x minus 18 divisible by x, let's say, minus 6, that's a question mark there. Well, I don't know. So I'd say this. Now, we know the top factors very nicely. In fact, this would equal x plus 3. Now, these are not integers, but the idea being this polynomial divided by that produced something without a remainder. Now, let's change that 18 to practically any other number, and I know I would have a remainder plus or minus. So then we'd say, no, it's not divisible, there's a remainder. So the concept of divisibility is really zeroes in on whether there's a remainder or not. So now we can define it formally, but it's also the notation we're going to use. So said that. Okay, make sure you're muted now, unless you're asking or answering a question. Obviously, you're going to unmute yourself for that. Okay. So we say that if b divided by a is an integer, okay, and by the way, the integer does not have to be a positive integer. I can have negative numbers. So don't dwell on positive and negative right now. If that is an integer, then we say then a divides b. That's how we would say it. A divides b. A is the denominator, and it is written a vertical bar b. Now, this is new notation for a lot of folks. In this context, a lot of times the vertical bar means such that. When I'm using set builder notation, we use a vertical bar for such that. In statistics, the vertical bar is used for conditional probability. Something happens with the condition that something else happens. So the vertical bar has many uses in mathematics. In this context, it means divisibility. And a lot of folks mistakenly use a vertical bar for a quotient, and which means that every time in your entire life you've used a vertical bar as a quotient, what you said was not only incorrect, but was actually mathematically impossible. because it's the wrong symbol in that context. Yeah, A divides B, and this means that A is the denominator, B is the numerator, and it also means that B equals AT for T an element of the integers. That's what divisibility means. There's an integer out there that I can do this. So we're going to go over some of the divisibility rules, and we're going to do some very, very basic divisibility proofs. So we first want to just get used to what the notation means. So if I'm given that A divides B, that means there is an integer out there that when I multiply it. Now, could A equal B? Is that possible? Could A and B be the same number? What do you think?
Yes.
Yes.
Because A times 1 would equal B. So a number clearly is divisible by itself. But there is something in this context, and this is not in the textbook, but this context, it also means that the absolute value of B must be greater than or equal to the absolute value of A. And the reason I'm putting absolute value is A and B can be opposite signs. So I don't want to use an inequality. Now, what the author actually uses inequalities in this case without absolute value, but says if we start with all positive numbers, then the following is true, but then also makes it very clear you don't have to be talking about positive numbers. I don't want to get dicey. So it means the size of B is at least as big as the size of A, right? Because again, they could be opposite signs. The number 2 does divide -2, but -2 isn't bigger than 2, but its absolute value is equal to 2. So that's why I want to make, this is a minor detail, but sometimes it makes it clear which way we're going here. So let's do the following. Start with something simple. If A divides B and B divides C, let's prove A divides C. I want to prove the transitivity of divisibility. Okay, given A divides B and B divides C, I want to prove that A divides C no matter what the numbers are. So I cannot prove this using numbers, but if this was not a true statement, all I would have to do is find one set of numbers that makes it false. And by the way, that will be something we look at as well, because not all statements are true. So let's start with what we know. Okay, the first statement says A divides B. Okay, so I'm going to write it like this. Since A divides B, there exists a T in the set of integers such that B equals A times T. Since B divides C, there exists, let's, how about, I don't know, running out letters of the alphabet. I can't think of 26 letters here. Such that C equals Q times B, okay? These two statements right here are straight out of what the definition of divisibility means. So now let's go to this statement right here. C equals Q times B, but what does that equal? That equals Q times A times T. Which is, how about if I rewrite that as A times QT? Are you with me so far? Now, what do we know about QT? How about I let R equal QT? R is an integer. Is QT an integer?
Yes.
Yes. R is an integer since integer multiplication and addition is closed. So what have we just shown? So C equals AR, therefore A divides C.
I have a question.
There's an integer out there that I can write this. B divides C, there's an integer out there I can write this. I do a little bit of simple algebra, just did a simple substitution. I replaced B with AT. Excuse me. Where did I do that? I did that over here. I replaced B with AT and then did a little manipulation. I used commutativity and associativity. Now, in the strictest sense, if you were writing a formal mathematical proof, you'd say, you know, first of all, I would do QA times T and then I'd move things around. I don't need you to explain commutativity and associativity of multiplication of real numbers. That's one of those ones that's kind of a gimme. We know this is equal to this by commutativity and associativity. Associativity is regrouping, commutativity is flip-flopping spots. And
Mr. Brown,
I always do that. Yes, question?
question. Yeah. So here, do we have to write this phrase since integer multiplication and addition? Because we have only multiplication here. Do we need to write addition every time?
I'm sorry. Yeah, you know what? Thank you, Sergey. I got kind of locked into what we were doing. Yeah, you're right. I don't need to write the addition part. Since integer multiplication is closed, let's take the addition out. You are absolutely correct. That's in this context, that's redundant. And by the way, we will be using addition also in some of these problems, because I'll give you a statement, then I'll give you a sum and say, is the sum, do we have divisibility? But yes, excellent point there. So I've just proved the transitivity of divisibility. Let's see. 2 divides the number 4 and 4 divides the number 16. Does 2 divide the number 16? Yeah, that makes perfect sense to me. Does everybody okay with that? That just makes perfect sense. Okay, let's try another one.
Question, Professor, before you fully erase the board, wouldn't it be C equals or A equals CR because A is the bigger number?
No, A is the smallest of the bunch.
A is the one that divides into
A divided B and then B divided C. So I give you an example. 2 divided
I just misread the division, this A and C in the division mark. I switched them.
Yeah, no,
very good. It makes sense. It makes sense.
Understand this. This is one of these things that's one of my pet peeves is when people write things, this particularly in an algebra class, they write things that are ambiguous. For example, when I'm writing a quotient, I write A over B. But I have students that, they write their quotients always this way, or it gets worse, they start writing it this way. Well, this is not a mathematical symbol. This should never actually show up in a mathematical context. This symbol is only used mathematically in one instance. Do you know the only instance the symbol is actually used? Percent. And percent is not a mathematical. You're right, 25%. In other words, we put little circles. This symbol was invented in the 1800s by newspapers, believe it or not, when newspapers were printing articles, because there's a thing out there that most of you probably aren't aware of. Your parents may remember this, but probably ask your grandparents. There was this old tool called a typewriter. Okay, some of us grew up using something called a typewriter, not a keyboard. A typewriter was this evil instrument that was very unforgiving if you made mistakes. For example, there was no backspace. Backspace and the delete bar are two of my favorites, by the way, just so you know.
I had one of those.
So anyway, when newspapers would be writing, 1/2 of the population got sick, whatever. If you ever use a typewriter, you'd get to the point, you'd scroll up, write the 1, scroll back, write the dash, scroll the other way, write the 2, scroll back, and then continue the sentence. It was extremely impractical to write an English sentence that included a fraction. So newspapers invented the symbol. That symbol did not exist, and it has never been a mathematical symbol in the history of the world. They invented it so they could write in one continuous line of text a 1/2. That's it. But the problem we have mathematically, and I'll give you the simplest example, because if you're a slash quotient person, that means that every time you write a slash, I'm guaranteeing you that 50% of the time you wrote it, your conclusion was actually incorrect based on what you wrote, because you forgot things like order of operations and such. You see, if I asked everybody to say 1/2 of X, here's what I get people writing, 1/2 X. Every single human being who writes a slash will write it like that. If I said the reciprocal of 2x, what does every human being who uses a slash write? 1/2x, which means every single human being using a slash just represented these as the same thing. Are they the same thing? No. X is in the numerator here, X is in the denominator here. Yet I'm totally ambiguous. If you're going to use a slash, you would absolutely have to use parentheses 100% of the time. And I've never seen a human being do that ever. But what people do in general when they use a slash is they put the thing you're multiplying by physically in the denominator every time. That X is in the numerator, not in the denominator. But if I put it next to the 2, I automatically put it in the denominator. But worse is I will have students, my favorite is when they're doing calculus and I'll get By the way, I'm not joking. I have like 10 quizzes turned in the last 2 days where this was square root of x. Now, tell me, how could any person write the square root of x as x to the 112th power? Which, by the way, I had 10 different instances this week of that. I have fun with this. I think we all agree that x to the 112th power is not root x. So why in the world would anybody write this? And I get this actually quite often. Because that's
if x is equal 1, we can say that.
no.
No?
How in the world could any person say this? Because this is how they're writing their 1/2. The smartest person I've taught this year, they're not in this class. I have a person who just never makes any errors whatsoever. And I had to point out to them, I go, you do realize you're writing an exponent of 112 when you mean 1/2. And you know what their comment was? That's the way I make my fractions. I'm like, oh my God. That's
I thought it's 112.
yeah, I know. That's what people, I'm getting people writing 112 when they actually mean 1/2, because they're writing 1 quotient bar 2. No, a vertical bar does not mean it's a fraction. A vertical bar, A over B. Right now, A is the numerator and B is the denominator. In this statement, A is the denominator and B is the numerator. So I said, you should never be using a vertical bar when you're writing a quotient, because the vertical bar a vertical bar is a statement, not a value. This is not a value. This just says A basically is a factor of B, or B divided by A is an integer. That's a statement. This is a value, but these are not. These are totally backwards, in other words. So let's try something relatively simple so we can start looking for counterexamples of things that are a little more complicated. Okay. If A divides B and A divides C, then A divides BC. I would like to prove this statement is true. And this is a good idea on every divisibility problem. Think of numbers. Okay, I did one in the last, I said 2 divides 4, 4 divides 16, therefore 2 divides 16. Okay, that makes sense to me. I want to have all my ducks in a row. I want to make sure someone said bigger numbers versus smaller numbers. A divides B. Okay, 2 divides 8. 2 divides 4. Does 2 divide 8 times 4? Does that seem reasonable to you, that would be a good conclusion? Hopefully. You'd say, yeah, I think that's probably a true statement. I did one example. That doesn't make it true, but it kind of tells me what order things are in. So in the first case, since A divides B, there exists R in Z such that what? Now I got to say it correctly. A divides B, then there must be an integer such that what?
B equals A multiplied by
Good.
R.
Perfect. Because the only error that I'm likely to make is that I'm going to put the R on the wrong side. And that's what we said before. When I say it in this order, generally you think of, okay, that's the smaller of the two. Yes, they could be the same number. R could be a 1. But generally you're thinking, you say 2 divides 4, you don't say 2 divides 1. That's not a true statement. The second one, since A divides C, there exists an S in Z such that C equals a S. Okay. Now what? I want to show A divides BC. Well, since B equals A times R and C equals A times S, what does BC equal? Wouldn't it just be this product?
Yep.
So I'll write it like this. I don't want an A squared. What do I want this to look like, actually? See, I wrote B as A times an integer. I wrote C as A times an integer. What do I want this to look like?
A times an integer.
A times an integer, exactly. Is that a true statement? Is everybody okay with that? That's big, again, commutativity and associativity of multiplication. Now, let's call it T. Let T equal A times R times S. T is an integer since integer multiplication is closed. So BC equals AT. Okay, I just wrote this product as A times an integer. Therefore, A divides BC. Crowd goes wild. Now that wasn't all that hard. You said that was not too bad. Divisibility proofs usually flow a lot like this because most of the time you're just dealing with multiplication. We can have addition. I can say A divides B, A divides C. What about the sum? Yes, the sum is a little more interesting sometimes because now I got to maybe factor, do a little bit of work. That's pretty easy. Not bad. Okay. Does anybody have any question before I erase this board? Okay. A divided one number, A divided a different number, A divided the product. That makes perfect sense. All right. I'm going to put something different down now. If A divides the product of two numbers, then A divides B and A divides C. That's pretty obvious, right? If A divides a product, then it divides each one. Or maybe not. What do you think? Can you think?
I think it's true.
I mean, a 2 divides I don't know, 2 divides, let's say 24. So 2 divides 4 and 2 divides 6. Yeah, that's true. But can you?
2 divides 50, but it doesn't divide 25.
Well, what's 50? 50 would be 2 times 25. Okay. I just used 24 just now, just to be simple. I said 2 divides 24. It divides 4 and 6. Duh. 2 divides 24, but I can write 24 as 3 times 8. Ooh, or worse, I can write 24 as how about 1 times 24. Oh, so here's one where we would want to come up with a counterexample. Okay, somebody said 50. Let's use 50. Okay, 2 divides 2 times 25. 2 divides 2, but 2, how do I say 2 does not divide 25? It's actually simple. Like that. So we have just proved this statement is false. By the way, this statement is true an infinite number of times. If B and C are properly chosen, I can make this true, but we've just found a really easy way to make it false. Okay, we found a counterexample. So if A divides B and A divides C, then A definitely divides the product. But if A divides the product of two numbers, it does not necessarily divide each of the two numbers. Aha. Okay, now here's another one. Is it possible, if A divides the product of two numbers, is it possible that it divides neither? That's an interesting question. If A divides the product of two numbers, is it possible that it divides neither number? Ooh, that's a tougher one.
1 times 1?
Well, no, but one that would work though. So
No, I don't think so.
that's a
It's
trickier one. Can you come up with a scenario where A divides the product, but it fails here and it fails here? Yeah, that's actually
6 divides into 12, but not. Wait, never
Oh,
mind.
no, keep going. 6 divides
6
4.
divides
Six
into,
does not
but
divide.
not divide by 3 and 4.
Or 4. Perfect.
Yeah.
There's actually an easier one. I'm lazy. 6 divides 6. But I can write 6 as 2 times 3. A number always divides itself, but it won't divide any of those factors that are smaller. Oh, okay. So we did it in one direction, but the other direction would not necessarily be true, meaning, simple English, the converse of a divisibility statement may not be true. Hint, 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 it's usually not true. Cool. Very cool. Now let's do one involving sum before we move on. All right. So now A divides B and A divides C. I want to prove that A divides quantity B plus C. Now I do need parentheses here. Okay, because I'm saying it divides that entire thing. And this is kind of a segue into what we're going to do some bigger problems in just a moment. Now, first of all, do you believe this is true? 2 divides 4, 2 divides 6. Does 2 divide the sum of 4 and 6? That seems reasonable. If 2 is a factor of the first number and 2 is a factor of the second number, then 2 ought to be a factor of their sum. I mean, I find that one totally reasonable. So I'm not going to spend time trying to disprove this one. I think this one is probably true. Now, there's one question people like in a math proof situation. When I say prove the following, I'm giving you an ironclad money back guarantee that that is a true statement because I'm asking you to prove it. If I say disprove the following, you already know it's not true. And now you just probably need to do a counterexample. The one we hate is determine if the following is true or not. Because now it might be true, it might not be true. And I don't go in with any preconceived notion. I've either got to prove it's true or disprove it, but I don't know which way it goes. We don't like that one, but actually that's the more powerful. Whenever you are told to determine if something is true or false. So if I give you a statement, it's determine if this is valid or invalid. Oh, that means I actually have to have reason. I can't just say valid or invalid. That's just a guess. I have to actually give some logical explanation. I'm saying prove or disprove this statement. But if you're looking at it going, that seems reasonable. I can't really think of any counterexamples that are just jumping off the board. So I'm going to try to prove it. Now, if it's not true, I won't be able to prove it, by the way. I will come up to a roadblock. But most statements of this nature are usually more obvious. You can see it. In Calc 3, when you're asked to find limits in 3 dimensions and stuff, you go, oh my God, I'm either going to find the limit or I'm going to find a counterexample. I don't know which way to go. Well, a lot of times you can just look at the problem and go, you know what? No, I don't think there's any algebra I can do on this one. I think it's not true. And I will attack it from that point of view. Or you say, no, I can do algebra. I can factor and cancel. I'm pretty sure it's going to be true. Most of the time, it's fairly simple to recognize. So since A divides B, there exists an R in Z such that, excuse me. Okay, this one starts the same as the last couple. Where are we? C equals AS. Okay, great. That's the given. I'm telling you these 2 statements are true. That's given. That statement means that this is true. That statement means that this is true. Now we will start the proof. We haven't actually done anything. We've just stated what's given. So now tell me about B plus C. B plus C equals A times R plus A times S. Huh. Well, that's A times.
Then you pull out the A, and then you do T equals R plus S, and then you have an AT.
So let T equal R plus S. T is an element of the integers. Again, the whole closure thing, since I know this gets redundant, but again, you got to do it because sometimes I might not be able to find that thing. Since integer multiplication is closed. I mean, that's not a long statement. Now, why is it so important that I say this? Because now I can say then B plus C equals A times T. Right now, this isn't the form of a divisibility statement. The form of a divisibility statement is that I found an integer where A times the integer equals my original number, therefore A divides B. A divides C because this is an integer. I have to have it in the form of a divisibility statement, which I now do. I'm almost done. I've did all the algebra. Now I need to state my conclusion, which is what?
I have a question.
Yes.
Could you? So we said let T is R plus S, and then T belongs to integer, but it's not multiplication, it's addition, no?
Oh, thank you. Gosh, Sergey, you are my
Sorry,
today. Why aren't the rest of you guys catching that stuff? Sergey's the only one. You're right, Sergey. This is when I want to use integer addition. It's close. Thank you. I get kind of locked in. Now, we've done everything we have to do But what should my conclusion look like? It should look like that statement right there, because that's what I'm trying to prove. Can I now say, based on that line right there, can I say this? Is that the logical conclusion?
Yes.
B equals A times an integer, therefore A definitely divides B plus C. And we'll put a big check mark. Yep, proved it. Done. A lot of times we do perfect work when we're writing a proof, but we fail to actually give the conclusion. That's one of the most common things when I'm emailing back to students with making comments on their quizzes. I'll say, you did everything, but you have no conclusion. Maybe you were doing something with truth tables and you perfect truth tables, and then you walked away. But the point was to determine if two things were equivalent, or if a statement was valid, or if I have a tautology or contradiction. So I got a truth table, but then nothing else. Well, there's got to be a conclusion at the end. This is either absolutely always true in every conceivable situation, or I found at least one counterexample where it wasn't true. I proved it's true. But so in other words, like, I got to have that guy there. Now, this is divisibility. This is not very difficult. Let's now do a specific problem. This is where it gets kind of fun, I think, personally. You know, I don't know, I could be wrong. Okay, let's do a very specific problem. I want to do, let's see. I want to do for K in the set of integers. I wrote it down, hold on a second. If n equals 2k plus 1, that would mean n is odd. Then, let's see, which one do I want to do? Then 4 divides let's see, make sure I got this right. That n divides 4n squared plus 3. I think I said that correctly. So for any integer k, n equal 2k plus 1, that's our definition of an odd integer. Agreed? So basically I'm saying, if I give you an odd integer, then 4 divides the square of that integer plus 3. Now, I can try examples all day long. Okay, wait, let's see. What if my n is 1? So 1 squared plus 3 is 4. Okay, that works. 3 squared plus 3, that's 12. Well, that works. 5 squared plus 3 is 28. That works. So I'll just run through all of the odd integers. That should do it, right? I'll run through all of them. That might take a little while. That might go into the next class, you know, when I go through the entire set of odd integers. This is kind of to convince myself that the statement is true, but I can't prove it's true by just trying odd numbers. But I should be trying a few, because what if? What if I pulled out an odd number? I put 13 and I did this and went, wait, it didn't work for 13. Well, then it's not true. Oh, so if I found an odd integer that made this false, that's all I need to do. But I'm looking at this going, you know, I think this is true. So I'm going to try to prove this. So I'm going to try to prove I have divisibility. So before I even start the problem, what should my conclusion be? Can anybody want to tell me what, if I do this correctly, what should the very last thing I write? If I'm trying to say for this, I want to show this.
Therefore.
Okay, so therefore.
N squared plus 3, or sorry, 4, and then the line divides into n squared plus 3.
Perfect. So everybody understands. This is what I need for my conclusion to look like if I do it correctly. Not words, but the actual mathematical statement that 4 divides n squared plus 3. Now I'm going to give you a hint. It is true. We want to figure out how to show it. So the algebra is not going to be intense. You know, as I said, n squared. If I made that a large exponent, that wouldn't be very fun, would it? Because then I'd have to raise that thing to a large power. So let's start with, okay, so let's start with something really easy. All right, okay, this is given. I don't have to prove this. So therefore, what is n squared plus 3 equal to? it's equal to 2k plus 1 squared plus 3. Okay. And what I want to get eventually is something where this looks like 4 times an integer. That then I can say that 4 divides. Well, just a little bit of algebra going on here. So that would be 4k squared plus 4k plus 1 plus 3. That's 4k squared plus 4k plus 4. Oh, I like the way that looks. Any ideas now, folks?
4 times
You take out
parentheses.
the,
Okay, yeah,
So what you're saying, factor out the 4.
right.
I now have at this point n squared plus 3 equals 4 times something. Now, there's something very powerful about the something. So let's let, what haven't we used? We haven't used t. Let t equal k squared plus k plus 1. T is an integer, so finally, Sergey, I get to use both, right? Since integer multiplication and addition, I've been wanting to do this all class, is closed. Okay, so what is true then? Then n squared plus 3 equals 4t. And that's what we needed. By the way, personally, I love proofs that involve therefores, because when you therefore, the next thing I say is the ultimate conclusion. A lot of times we'll use, thus, and we use all sorts of different words because we're not quite done. But therefore is kind of this completion. I've said everything I need to say. If this is true right here, therefore 4 divides n squared plus 3. And I have proven what I need to prove. This is verbatim how this proof goes. There's no additional things I need to say. There's nothing left out. So this type of divisibility problem is kind of fun. It's kind of simple. And you're going to be dealing with stuff like this. I've asked you a question like this on the quiz. It's not complicated. But what if it's not true? That's the tricky part. What if I gave you something that was not true? Well, today I'm not that concerned with the not true. We're actually going to look at that, I think, tomorrow. If I added 4 to this, if I said n squared plus 7, or n squared plus 11, or n squared plus 15, or n squared minus 1, or n squared minus 5, if I add multiples of 4 to this, do you suppose this statement will still be true?
yes.
Yes. That hopefully that's a no-brainer. Oh, I have a number that's divisible by 4, and now I add any multiple of 4 to that number, it's still divisible by 4. Therefore, if I add positively or negatively, if I add any number to here that's not divisible by 4, like I add 5 to this, or 11 or something, then the statement would be false. Hopefully you agree with that. If I've just proved this is true, then n squared plus 4 would make the statement false. So how would I prove that in general? Oh, see, when you're talking about divisibility rules, you're saying, well, is this statement true? But what if I said, I want to show, I'm going to make a statement. I want you to show it's always false. Can you show something's always false with a counterexample?
No.
No. And here, I'm going to give you a simple example. I always do this in remedial level classes when I'm introducing logic, and I say, it's difficult to prove a true statement is true sometimes because there might be an infinite number of occurrences. But it should be easy to prove a false statement is false because you only have to show one example. So I always like to use the statement, all trees have leaves. So you want to prove that's true. So you go around San Diego, you're just driving around neighborhoods, and every tree you see has leaves. You decide to fly across the country. You're looking on the East Coast. You've viewed tens of thousands of trees over the next several weeks, and every tree has leaves. You're going, well, I guess the statement is true. Well, show up in, around November, December. And my next door neighbor, all of their leaves will be in my front yard. They won't have any more leaves on their tree. You found a tree that didn't have leaves. Finally, you can prove that statement is false because you found one tree. That's all you got to do is find one tree. If the statement is all trees have leaves, you have to find one tree that doesn't have leaves to disprove it. But if I said prove all trees have leaves is always false, now what's the burden on you? To find one tree? Think about that. I want to prove a statement is always false.
All the trees, right?
Yeah, you would have to show that all of the trees are leafless, if that's a word. It's like Legolas, I guess, leafless. That's a much more difficult thing. So if I was trying to show something, I'm trying to say, is this statement true or false? I found one occurrence where it's false. You go, great. That's not the same as saying show the statement is always false. Ooh, that's a more powerful thing. That's something we're going to do. Not today. So if I put an n squared plus 4, I'm pretty sure we would all agree that I'm going to get to the place where it's not going to be true. Mostly I'll give you a hint because at some point I won't be able to factor out the 4. I'd have fractions. I'd have something in there. And remember, we talked about the whole remainder thing. So that's our segue into the next thing. The next thing is a little bit of notation. It's a simple concept, but it's notation that is used universally. In fact, if you're a programmer, you might already know these terms. Okay, we're going to talk about the next thing, the terminology. Let's see, what is the exact term they use? I want to use the exact same language. They oh, that doesn't really say. Okay, generally it's just generically referred to as the quotient remainder theorem, but that's so ambiguous, that title. This has to do with divisibility rules and such. So if I give you, and by the way, we're only dealing with integers here, but they can be positive or negative. So if I ask you to deal with the quotient of two integers, either there is a remainder or there is not. Okay, so we start with something simple, but let's make sure we understand. When I did 20 over 4, we can write that as 5. Okay, that means that 20 equals 4 times 5 plus 0. If I said 21 over 4, you said that's 5 1/4. That's equivalent to saying 21 equals 4 times 5 plus 1. You know, in a upper level algebra class, we say the remainder is 1/4. But in lower level classes, didn't we often just call that the remainder? That's how much was left over. I didn't write the answer as a fraction. I said, okay, so another way of saying it, in English, think little kids now. 4 goes into 20 5 times. 4 goes into 21 5 times with 1 left over. Okay, I have a box and I have 21 big items and I can only get, let's say, 4 in each box. I have 21 items. I got 4 in the first box. I got 4 in the second box and so on. Oh, I have 5 full boxes with 1 item left over. When you have your 1 item left over, you don't say I have 1/4 of a box left over. You say I had 1 item left over because I'm not subdividing the 1 item. So this language actually, from that standpoint, makes a lot more sense. Oh, I put 4 items in each box. I filled up 5 boxes. I had 1 item left over in this case. In this case, I filled up 5 boxes. I didn't have anything left over. Great. So the numbers that we're dealing with here, okay? So in general, if I wanted to do a quotient, we call this guy here, okay? He is called the D. Let's see, I'll write it here. This guy is called D in both cases. That's my divisor. And that's it's also my denominator, it doesn't matter. My divisor and my denominator in this case are the same thing. I'm dividing by that number. What's 5? Well, if I said 20 divided by 4 equals 5, in simple English, 5 would be the what? Starts with a Q.
Quotient.
The quotient of 20 and 4. So we call 5 the Q. In both cases, we call 5 the Q. Now, I had nothing left over. Here I had 1 left over. In each case, what would we call this number? In each case, we call that
The remainder.
The remainder. So the quotient remainder theorem is essentially any time you're dividing a number, and we'll call this guy n. So n over d, okay, is equal to what? It's equal to Q, I'll put with remainder R. Q for quotient, how many times did it go in? Okay, so in this case, I'd say with the remainder 1. So then ultimately, what does N equal? It equals DQ plus R. This is an absolute mathematical statement. Now, we have to be a little bit careful. What if? And I've seen people do this. I'm going to give you a really goofy what if. 4 goes into 21 3 times, and I've got 9 left over. Now, mathematically speaking, is that statement correct mathematically?
Yes.
But would you say 4 goes into 21 3 times with 9 left over? Would anybody say that?
No.
That's something. The leftover is what's throwing us here. Yeah, the remainder has actually very, very specific rules. The remainder cannot exceed the denominator. So R is bounded at the lower end by 0. What do you think is bounded on top by?
The divisor.
Exactly.
Has to be less than it, or
Okay. So if I said 20 over 4, is that a correct mathematical statement right there?
Yes.
Yes, but wouldn't it be easier to just say this is 5 and no remainder? Wouldn't that make more sense? So the 4 we're treating as our remainder. 4 can't quite reach. I would stop writing remainders. 20 divided by 5 is, 20 divided by 4 is 5. 21 divided by 4 is 5 with 1 remainder. 22 divided by 4 is 5 with 2 remainders. 23 divided by 4 is 5 with 3 remainders. 24 divided by 4 is 5 with 4 remainders. No, 24 divided by 4 would be 6. So when I'm dividing by 4, what's the biggest remainder I can possibly have?
3.
3, because if I got one more, so it's bounded by what?
Has to be less than the divisor, or divided by.
Remember, these are integers, so I can actually say very specifically, okay, now. Is this true mathematically? Is this a true statement?
Yes.
Yes.
So would I say that that's my Q and my R is -3?
No.
No, because I can't have -3 left over. I mean, there's just something wrong with that. I had 21 items and I can fit 4 in a box. I have 6 full boxes and then I have -3 left over. I can't have -3 left over. That doesn't even make sense. Remainder cannot be negative. So that statement, although mathematically correct, that can't be my Q. -3 cannot be my R. Okay, so you say, well, that's not difficult. Well, where this gets a little bit tricky, how about if I'll use different numbers just so we don't get confused. If I said, let's say I'm going to give you N is 32, I'm going to give you D is 6. I would like you to write it in this form. Can anybody do that for me? It's a simple exercise. So you're going to say 32 equals, well, simply
5.
how many times does 6 go into 32? It
5
goes in,
times.
with how much left over?
2.
2. Beautiful. That's perfect. That is the answer. Okay. Oh, well, we're doing this in high-level mathematics. Yeah. All right. N is -23 and D is 6. Okay. Negative 23 this time.
So would that be -4 plus 1? Wait,
-3, right?
Is that what you said? Well, that seems kind of a crazy answer. Does anybody like that answer? Does anybody like that answer?
Yes.
You should, it's correct. Wait a minute, but 6 goes into negative 23. Shouldn't that only be 3 times? But then I would have plus -5. By the way, algebraically, is negative 23 equal to 6 times -3 plus -5? Is that true algebraically? Yes. So why is this not the answer? Why is this the answer and not this?
Because of that rule you just said.
Oh, that's why this is so important. Algebraically, this is a true statement. But based on our definitions, right? I can have a negative quotient because I had a negative numerator. That's not the problem. This is one that gets everybody. My remainder has to be +1 because -24 plus 1 equals -23. That's true. And this number here is between 0 and what? 6 minus 1. Okay. Now, by the way, the divisor will always be positive. My numerator can be positive or negative. My divisor will be always positive. Okay, because otherwise this statement here wouldn't work, would it? If D were allowed to be negative, then this is an impossible mathematical statement. So, okay. Now that we have this is an exercise. This is not hard. Now we're going to define a couple words that some of you may have heard before. Words. They're mathematical terms. Div and mod. Now, be honest, has anybody ever heard these terms before? Div and mod.
Yeah,
Yes.
they're used in programming.
Good. Because that's if you're a programmer, you may be familiar with those. Div and mod is exactly what we just did here. Oh, but which one applies to which? So when I say n equals d times q plus r.
I think mod is R.
This is the div. This is the mod. Oh my goodness. Div and mod. Well, but I thought the divisor was D, but how many times the divisor went in is the div. What you have left over, if anything, is your mod. Oh my goodness. Now, does anybody know what divisor, that makes perfect sense. What does mod come from? Because there's actually a lot of math words. There are several math words that start with mod that have nothing to do with each other.
Modulus.
Modulus.
Modulus has to do with, anybody know? I said z equals a plus bi complex number. That's true. That's called the modulus. Modulus is basically the distance from a complex number on the complex number plane to 0. So it's not modulus, but you're close.
Modulo?
Modulo. Totally unrelated. These have absolutely no connection. In fact, they're not even in the same universe of mathematics. Modulo, we're going to do this a little later. I always like to think of modulo, I call it clock arithmetic. Now think of a clock. Now I don't mean your digital one on, the clock with the hour hands and it goes 1 through 12. So if I said, okay, right now, I don't know what time it is. Hold on. Right now it is. Oops, it is 8:57. Okay. Not military time, 12-hour clock. Okay, it's 8:57. Exactly what time is it going to be in 12 hours?
8:57.
Okay, that was pretty easy. Okay, in 24 hours, 8:57. All right, in 1 hour, 9:57. Okay, in 7 hours, 15. No, wait a minute. Not 15:50. It would be 3:57. It would start over. In other words, div and mod apply to things like a clock. The only difference is in a clock, I don't have a 0 o'clock, I have 12. So the clock's a little bit off. But if I gave you multiples of 12, wouldn't you always be at the same time? So if I gave you a number, what you do, so if I said, for example, what time is it in 30 hours? Would it be the same time as it, again, not AM, PM on the clock. In 30 hours, wouldn't it be the same time in 18 hours? And wouldn't it be the same time in 6 hours? Do you agree with that statement?
Yes.
Yes.
And the same time 6 hours ago. Why? Because that 6 is the mod. It's what's left over when I divided by 12. Oh, so if I said 6 hours, 18 hours, 30 hours, 42 hours, 54 hours, it would always be the same time. It would always be the same time on the clock because the mod would be the same. Now this, we're going to discuss this type of mathematics a little later. It's actually pretty big and pretty powerful stuff. This is the intro. We do that stuff a little bit later in the course, which in this case means like a couple of weeks. So now I want to change the language slightly. And I want to make it simple. All my pens are starting to run out of ink. So if I said this, 24 div 5, 24 mod 5. What I'm asking for in this case is the Q. What I'm asking for in this case is the R. And someone said that earlier, you're absolutely correct, but we're formally defining it. By the way, there's no problem that should really challenge us. Heck, if I want to be ultimately lazy, I just use the fraction key on my calculator because it converts everything to mixed numbers. So how many times does 5 go into 24? How many whole times? 4 times.
4, sorry.
So 24 div 5 equals 4. You don't have to say the Q, but in the QDR thing, it's the Q. When I put 24, excuse me, when I say 24 divided by 5, what is my remainder?
4.
It's also 4. Oh, okay, that's interesting. All right, let's do another one. I've got 32 div, let's say 7. I have 32 mod 7. So now the answer is just simply a number. Okay, it's not a difficult thing to do, but you have to know why. 32 div 7, and but you can do this in your head. Hopefully, if the numbers aren't big, you should not be challenged. How many times does 7 go into 32? If I was doing long division, 7 goes into 32 4 times. It has a remainder of
4.
Did I do the same thing again? Oh, all right. I'm sorry. Let me change that. Let's make that 34. I got to be more clever than that. I'm just making up problems at random. Sorry, I don't want to get the same value twice in a row. That's okay. 6. Now it'd be 6. Now, how do you justify this? Because 34 equals 7 times 4 plus 6. There's your justification for both answers. Now, I could have only asked you the first question. I could have only asked you the second question. This would be your justification because in the first, by the way, let's say I didn't ask you the second question. I only asked you this. You can say this, and that's where my answer came from. Now, forget that. I only asked you the second question. Then you'd say this because that's where my answer came from. So that's the easiest way to think of div and mod because more often than not, you're only going to be asked one of the two. Now let's do one more challenging. Let's do one involving a negative number. So I've got negative 23 div 8.
Before with a remainder 1 or negative 4, sorry.
3, right?
Negative 3. Yeah. Negative 3.
Wait, by the way, that you go, wait, 8, but 8 only goes into 23 2 times whole, but then I get, so Negative 23 equals, you said, I'm sorry, you said 3 or 4?
Negative. I said 4 at first, but they corrected me.
So what should it be? Is it
Negative 3
negative, but it's negative 3
plus 1.
plus 1. So therefore your answer is negative 3. And by the way, always do this because now you have absolute certainty. That's if I don't do this and I have a wrong number here, that's common, then it appears just to be an absolute blind guess. So similarly, if I had said negative 23 mod 8, you'd say the answer is positive 1 for the same reason. Usually I'm only going to ask you one. I'll just say number mod number or number div number. What is it? Because if you understand how to find one, I'll give you the benefit of the doubt. You knew how to find the other. The negatives clearly give us a little more issue. All right. Is a fun one.
0 and 6.
You guys like that answer? That seems crazy. I can have an answer of 0. Well, let's justify that.
If the D equals 8.
Is this a true statement? Does 0 equal 0 times 0 plus 6? I'm sorry. What am I saying? I said that totally wrong. Hold on a second.
6 times 0 plus 6.
Oh, I'm
6 equals, right?
all right. 6 times that. I'm looking at this. So is that, look at the part in orange. Is the part in orange true or false?
No.
It's true.
I'm sorry. Yeah, you see the, yes,
This true or false?
true.
So does anyone want to change their answer? Is that 6? Is this 6?
No, it should be 0.
It's 0. Ah. By the way, it seemed reasonable, so I wrote down what you said. That's why I said always do this. Oh, now I can clearly see. Yep, they both turned out to be 0. That was a trick question. You know that was a trick question. All right, last one of the day. 7 div 12, 7 mod 12. Although this is probably just as confusing.
I think that is,
What I would do before I try to write either one of these answers, I'd try to write, 7 equals. What? This is my D, remember?
12 times 0 plus 7.
True or false, everyone? These automatic. You don't have to think about these, right? That's my D. That's my N. Is this true mathematically, that statement?
Yes.
Yeah.
So in English, I'm saying 7 divided by 12. That's 0 with a remainder of 7. I think that's what somebody was thinking about in the last example. They saw that and they put that.
Yeah, I swapped them around. I don't know why I swapped the 0 and the 6.
No, by the way, it's okay to make mistakes now. Just don't make them later. We'll have a whole rash of timeouts and things like that. All right, this is where I wanted to get to. This is fun math, and there's nothing about this that should be challenging, but you definitely need to do a few problems, get the hang of it. Div and mod turn out to be really, really important concepts, but from a numerical standpoint, they're absolutely trivial. I mean, every problem we just did, I think everybody had an easy time doing it in their head, but because of the definitions, we have to make sure we get it correct. So my strongest suggestion is always start with this before you answer any question, just to make sure you're looking at the proper part.